Let's take a look at example 4. They ask us to find the upper and lower sums for the region bounded by the graph of f of x equals x squared and the x-axis between x equals to 0 and 2. In order to get a start on this problem, let's go ahead by graphing it. So we can kind of see the region we're looking at. We know the graph of x squared looks like this. From x equals to 0 to x equals to 2. At x equals to 2, x squared has a height of 4. So this would be the region that we're looking at. What we are going to do is we are going to break this region up into a collection of intervals. This is going to be our delta x. So the width of each interval, kind of like what we saw with the last problem. In the last problem, they gave us a fixed width of 2/5. Here, we're always going to break it into n pieces. So it's going to be b minus a divided by n, where b is the right endpoint of the interval and a is the left endpoint. So this is going to be 2 minus 0 divided by n, which will be 2n. So each interval here will have a length of 2 divided by n. Let's start off by doing, let's say, the lower sum first. If I look at a rectangle in this region, the lower sum would come from the inscribed rectangles. We know that the width of this rectangle is going to be 2 over n, and its length is going to be given by the height of the function, which is going to be evaluated at the left endpoint. So for this particular problem, the left endpoint is going to give us the lower sum. What are our left endpoints going to be? Well, let's call the left endpoint in this case xi, because we're going to have a lot of them. We're starting at 0, would be the first one, and then if we try to index it with I, we would add I minus 1 times 2 over n to get to the next one. When I equals to 1, this term would be 0, and that would give us the first endpoint, left endpoint, which would be 0. And then if we add 2 over n, that'll continue to give us the rest of the left endpoints. So our xi here, the thing that we would be evaluating into the function, would be I minus 1 times 2n. And then just like what we saw last time, the area, if we add up all of these rectangles, the area is equal to the sum from the first rectangle up until the last rectangle. It's going to be the sum from I equals 1 to n of the length times the width. That's the sum from I equals 1 to n. The length is the 2 over n. Or maybe that's the width, because it doesn't matter. It's interchangeable how you view it. But the length, I said a moment ago, I believe, was the height of the function. So that's going to be f evaluated at xi. That's the function evaluated at each left endpoint times the 2 over n. That is, this is the sum from I equals 1 to n. I want to evaluate the function at xi. We said the xi was I minus 1 divided by 2n times 2n, where our function f of x is equal to x squared. So this should be equal to the sum from I equals 1 to n of I minus 1 over 2n squared times 2n. Let's simplify the sum. This is equal to the sum from I equals 1 to n of I minus 1 squared times 4 over n squared times 2 over n, which is equal to the sum from I equals 1 to n of I minus 1 squared times 8 over n cubed. Notice that with respect to the index of summation, this term is a constant, so we can use our constant rule to pull that outside the sum. This is the sum times 8 over n cubed from I equals to 1 to n of I minus 1 squared. If we expand that, that's I squared minus 2I minus 1. This is equal to, from here, now this is where we're going to apply those sum formulas we had from the previous section. Let me see if I can add a page below. So where are we at right now? We have this. We have 8 over n cubed times the sum from I equals 1 to n of I squared minus 2I plus 1. I hope I had a plus 1 on that last part. So that's a sign mistake. Negative 1 times negative 1 is positive 1. We can split this sum apart, so let me not forget that we're going to have this 8 over n cubed. This is going to be on the outside of this whole expression, and we're going to have the following. The sum from I equals 1 to n of I squared. I could factor the negative 2 out. The sum from I equals 1 to n of I, and then plus the sum from I equals 1 to n of 1, which is a constant. From earlier in this section, we have a summation rule for each one of these. For example, if you go back through your notes, the sum from I equals 1 to n of I squared was n times n plus 1 times 2n plus 1, all divided by 6. The sum from I equals 1 to n of I, that was n times n plus 1 over 2. And then the sum of a constant is just n times the constant. So this is going to be 1 times n, which is n. From here, we can go ahead and try to simplify this. See, what do we have? We have 8 over n cubed times n plus 1 times 2n plus 1 over 6. Here, these will cancel. So we have negative n times n plus 1 plus n. From there, let's try to see what we can do. Let's distribute the 8 over n cubed term in. That'll give us an 8 n times n plus 1 times 2n plus 1 all over 6n cubed minus 8n n plus 1 over n cubed plus 8n over n cubed. if we simplify this, here's what's going to happen. You can cancel an n with here and here, so I'll leave us an n squared in the denominator. A 2 can go into both of those. 2 goes into 8 4 times, goes into 6 3 times. So that's going to leave us with a 4 over 3. We're still going to have an n squared in the denominator. And then our numerator, if I expand that, if I expand n plus 1 times 2n plus 1, that should give us 2n squared plus n plus 2n would be plus 3n plus 1. Minus, this is going to be an 8. One of the powers of n will cancel, so I'll have an 8 n plus 1 over n squared plus 8 over n squared. And we could reduce a little bit more for this if you wanted to. If you expand terms and whatnot, it's going to work out reducing to this. You're going to have an 8 thirds minus 4 over n plus 4 over 3n squared would be our expression for the lower sum. If we go back, we could do this for the upper sum as well. I'm not going to work through all of this, but let's at least get the setup part of it down. If we wanted to do the upper sum this time, the only thing that's going to change is our xi values. So we would need to start, first of all, at 2 over n. That would be our first one. And then it's, as I would change, it's just going to be 2n times I would be our representation of our right endpoint. So this would be the sum from I equals to 1. I should say the approximation sum, not the final answer. This isn't the area of our region. This is just the approximation using sums. This would be the sum from I equals 1 to n of the length, which we said was f, evaluated at xi, times the width, which in this case is going to be 2 over n. This is the sum from I equals 1 to n of the function, which is x squared, evaluated at 2 over ni times 2 over n. This is the sum from I equals 1 to n of 4 n squared I squared times 2 over n, which is the sum from I equals 1 to n of, what did we have there? Let me just go back and look. It's going to end up being 8 over n cubed times I squared. With respect to the index of summation, this is a constant, so you could bring that to the outside. That's 8 over n cubed, the summation from I equals 1 to n of I squared. We're almost there. Might as well just go ahead and finish this one off. This is going to be 8 over n cubed. The formula for the sum of the first n squared terms is n times n plus 1 times 2n plus 1 all over 6. And then algebraically, if you were to go through and simplify this, what we would get would be as follows. It's going to end up being 8/3 plus 4 over n plus 4 over 3n squared. And this would be the representation for the upper sum. What we are going to see is that as n increases, in other words, as we use more and more and more rectangles, these upper and lower sums are going to get closer and closer and closer, and they're going to approach the limit, which will be the real area of the region.